this presentation. So, okay, well, 1 minute. Okay. So, yeah, I'm Gaétan Raynaud. I'm glad to be there today to talk about my work during my master thesis. This is about the study of physics-informed neural networks to solve fluid structure problems of turbulent-like phenomena. So I've worked with Professors Frédérick Gosselin and Sébastien Houde, and we're also supported by a consortium on hydraulic turbines, which is called TR Francis. And this consortium is interested in the vibration in hydraulic turbines, especially the fluid structure vibrations, because today the production of electricity relies also on intermittent sources like windmills or solar panels. And to deal with this intermittency, we can stop the hydraulic turbines when there are enough production with the solar panels and the windmills, and we can restart them again when this is not enough. We can also make these turbines spin without loading them. But in any cases, these new modes of operation, they can cause severe vibrations, as it is reviewed by Trivedi and others, especially for Francis turbines. And this vibration can then cause damages, which are expensive and can be also dangerous for human beings. A way to tackle that issue is to look at digital twins. The concept behind this is that we got our actual system, and then we make a virtual copy of this system that we call the digital twin. And this virtual copy is updated with sensors directly installed on the actual system, so that while it is running, we get information on the behavior of that system that we use to update our simulation. And on that virtual copy, we can perform prediction of fields like the damages of that structure. We can also perform predictions of which operating mode, what is the impact that an operating mode will have on that system. And in the end, we will use that information to use the actual system in a better way, and also plan predictive maintenance to help reducing the cost. The problem with digital twins is that classical numerical methods have some problems to deal also with large amounts of data from sensors, numerical solution from equations, and other types of these words. And the idea in this master thesis is to examine if physics-informed neural networks can be a good candidate to one day answer these needs. So I'll start by a bit of historical context on physics-informed neural networks. So the underlying principle was first described by Disanaki and Fentian in an article around 1994, and then by Lagares and others around 1998. And to our knowledge, for nearly 20 years, there have been no scientific production on that topic. And in 2018-19, Raisi, Perdikaris, and Karnadakis really kicked up the scientific production with this paper that really emphasizes the fact that with pins, you can do inverse problems as well as direct problems. And since that, the numbers of paper each year around 2018-19, it has really started to skyrocket. And in dashed line, it's the prediction toward the end of 2021 if the pace stays the same. So this is really exciting to have this scientific production in this very narrow topic. But the other part of that is that it lacks of maturity if we compare to other classical numerical methods like finite element, finite difference, finite volume, and others. And we still need to gain confidence on the capacity of pins to solve these problems, and that was also one of the aspects of this thesis. So I'm going to illustrate also what's possible to achieve with pins with two examples. The first example I've chosen is provided by Kaz and others in a paper published in Journal of Fluid Mechanics this year. And in this paper, they proved that how they're able to reconstruct a field using indirect measurements. The exam they take was a cup of coffee, with hot liquid inside, and due to the difference of temperature, this hot coffee creates a flow of air upward. So the hot air starts to going up, and to understand which is quantitatively the flow field that we can observe, they measure the temperature field on several planes that you can see there, and from that, using the links in the Navier-Stokes equation between the temperature, the pressure, and the velocity, they were able to reconstruct the three components of velocity as well as the pressure and the temperature, which are unsteady and three-dimensional fields. And also, there is no boundary condition absolutely on that thing because we cannot control the boundary on the physical domain, because it comes from experimentation. So that's quite interesting to be able to infer the overfield that you are not able to measure directly. Another illustration for my colleagues who work in structural dynamics and we perform mechanical tests, sometimes on parts that can have a complex patterns, and sometimes also with materials that are still to be characterized. When you perform these mechanical tests, you are not always able to measure for instance, the deformation field, which is highlighted there everywhere on the part. Sometimes it's only on the sub part of the piece. I've highlighted only the center part. And the idea with PIN is that if you got sufficiently information, you can recompute the complete field of deformation on the total part, but also other fields that are related, like the stress, the damages, etc. And also, you can, in the same time, identify some parameters of the model. For instance, it can be the Young modulus, it can be the Poisson ratio, or more complicated constitutive relationship, like it is illustrated there. And this with only experimental data that can be also imperfect, and we'll see that in a few slides. Okay, so the two last examples that I've presented there are perfect examples of inverse problems, and these are opposed to direct problems. So usually you perform a numerical simulation on a certain domain that you're able to know and discretize, for instance, with a mesh. On that domain, which is bounded, you have boundary conditions that are clearly identified, and also initial conditions, which is a given state of the fields of your variables at a certain time, usually the beginning time. Then on that domain, you know the physical principle that you are going to apply. For instance, the conservation of mass, of momentum, of energy. And finally, you know the materials property that you are into your problem, into your simulation, like the viscosity of your flow, the Reynolds number, the Young modulus, or more complex constitutive relationship. It's also the case for turbulence modeling when you're doing Run's equations. So once you got all these inputs, you put them into a numerical solver that reconstruct the complete field, that solve the complete field. And from that field, you extract meaningful information like quantity of interest, which can be, for instance, an average forces. You're designing a plane, you want to know the lift or the drag of your wing, etc. You can design an engine, you want the efficiency of that engine, and that's what you get at the end of the numerical simulation. But when you are in the design process, actually, this is expressed in a different way. You got a target that is expressed as a quantity of interest, and to reach that target, like you design the plane, you want a certain lift. To reach that lift, you can change the parameters of the inputs of your simulation. For instance, you can change the geometry, the boundary conditions, you can change the parameters that you are using into your model, like the materials actually. And you cannot compute directly into one direct numerical simulation the initial inputs so that you get the outputs. You have to do an initial guess and then optimize iteratively these inputs and perform successively direct simulation, which is quite prohibitive in terms of computational cost. The idea of physics-informed neural networks, is that they perform the optimization of the inputs and the solution of the field in one and only optimization process, which can be quite practical for inverse problems. The other aspects, which is quite different with physics-informed neural networks, if we compare it to finite elements or other numerical methods, more classical, is that they use different methods to approximate the solution. Especially, they rely on neural networks. And neural networks, they use the generalization of regression model. So when we're talking about regression in a model, we usually have in mind that we have a sample of points that stands for a phenomena that we capture through discretized measurements. So here, X is in the input and Y is the output that we directly measure. And one of the simplest models that I think we all know is the linear one. So this is the simplest model, Y equals AX plus B. But you can see there, and I think in many applications, that a linear model is not enough to get the fundamentally nonlinear phenomena in the nature of phenomena. To tackle that problem, to address that problem, neural networks, they use nonlinear features. For instance, they use nonlinear function, which is called the rectified linear unit. This is basically a threshold. So for negative inputs, it's 0. For positive inputs, it's just identity. And we apply this threshold to the scale and shifted input. We apply, so we have sigma of y1, and then we redo another scaling and shifting. And with that model, we performed an approximation of this data with a far better accuracy. So you can see that the choice of function, the choice of parameters here have a matter. And so to increase the precision, we can add another set of nonlinear features, which concretely increase the depth of the neural network. So the more nonlinear activation function and layers you got, the more deep is your neural network. Another possibility is to increase the size, to increase the width of your neural network by using here vectors instead of scalars. And then your A and B will be with matrices and vectors. And in the end, when all these scalar coefficients are defined and are known, you got an approximation y of the input x, which is a symbolic function. So it is defined everywhere and you don't need a mesh. And to illustrate that and to compare it to other methods of approximation, I choose an arbitrary function that could be a solution of a given PDE of the partial differential equations. And let's see how it compares with other approximation methods. So the most basic one, in my opinion, is to use a grid. So I sample 10 points in that segment. And on these 10 points, I store the value of the function. And I approximate my function with step function. So it's only constant by part. And here you see the error that I made using that techniques of approximation. If I want, so you can see that the approximation is not that good. And if you want to increase the precision of that approximation, we can tune the position of our grid. That's what we do when we are doing adaptive meshing, But still, we got large errors, especially in this area. Another method is to use functions that are one order higher, for instance, linear by parts, and then the precision increases, and we can also adapt the mesh. But we still rely on grids. Slightly different methods are called spectral methods. Actually, they use a linear decomposition of basis function. And here I provide an example with a Fourier content. So it's a basis of sine and cosine, and I have still 20 scalars that help me perform this approximation, which is an increase in precision compared to the other methods. And lastly, the multi-layer perception, which is another name for the neural networks, it performs this approximation with only 19 scalars and with this expression. So here you can see that for 6 intermediate variables, I perform an affine transformation. Then I apply my nonlinear function, which is hyperbolic tangent, and then I use a scale and a shifting to perform this. And here is the error which I obtain, which is 2 orders of magnitude lower than the one with the step function. Okay, another main difference between this approach and the other, like the step function, linear functions, and Fourier content with the spectral methods, is these coefficients, the B2, B1K, A1K, A2K, you cannot obtain them with a direct projection. For obtaining this, especially the ones that are inside the nonlinear function, you have to perform optimization of the parameters, and that's one of the main differences between PINs and these things. Okay, so here we discuss about the approximation by neural networks, but in a physics-informed neural network, there is physics-informed. And this means that we perform not only approximation with data, which is in that part of the equation where we know the value of the function at some location, but we also perform the approximation because we know some physical principles that are encoded mathematically with differential equations. And that's that other part of the loss function that we create. So here is the approximation by the neural networks, the structure of the neural networks, and theta are all the scalar parameters. This is the output. So we compute a part of the loss with the data and another part with the equations. And to give you a concrete idea, I illustrated here an example in TensorFlow, which is written in Python. So at that line, we compute the output of the neural networks. X is vectors of position, and U is the same vector, but with the values of the output of the neural network for each position. And then at line 10, here you can see that we compute the exact derivative of U with respect to X at each location inputted in X. And this is very practical. This is done in a fixed number of operations because this graph of operation is symbolic, and we can perform automatic differentiation directly in most of the modern machine learning libraries, and this is the case with TensorFlow. And you can do this derivation as many times as you want. For instance, here I get the second order derivative, and once I got all the derivative in my equation, I can sum all the terms. I can also sum nonlinear terms. For instance, I could have UXX times U, for instance. And here I got the residuals. I take the square value, the average, and that is directly my other part of the loss, which is physics informed. Another detail, which is, I think, quite interesting at that point, is in these residuals, in this example of residual, there is gamma. Gamma, typically, it's the Reynolds number. It's the Young modulus in an equation of the mechanical. This is the parameters of my materials or of my model. And I can know that property at the beginning of the training, but I can also set up as a variable that will be optimized with all the other variables in my neural networks, so that this is very useful for the identification of parameters as discussed earlier. Okay, a few words on the optimization because it's part of the approximation by pins. So my solution is defined by a set of scalars. We refer to that set of scalars by theta. And the objective of the problems is to find these parameters that minimize the loss. And the problem is that in the previous example, we got only 19 scalars to optimize. But in actual problems like in 2D, 3D flows, and 4D dimension, if you add time, the numbers of parameters to approximate, to find, to optimize, it's more like 1,000, 10,000, 100,000, maybe 1,000,000. So you cannot directly just split some points in every dimension and take the best option because it's the numbers of possibility grows with the exponential of the numbers of parameters, which in that case, it's just too big. So to do that, to solve that problem, we perform gradient-based optimization. The idea of that is the loss function, if you look in only 2D, it has a certain shape, and we want to go to the position in the parameter space where the loss function is minimum. So we initialize randomly the parameters at the beginning of the training, for instance, there, and we follow the direction of the gradients of the loss with respect to the parameters. This is this thing. And once again, which is practical, is that this quantity is obtained exactly in a fixed amount of operation thanks to automatic differentiation. And you got the example of how it is inputted into the code with the gradients of the loss with respect to theta. And in theta, there is the parameters in the neural networks, but also the parameters that you want to identify, like the Young modulus, the Reynolds number, etc. Okay, I won't go into much details, but we have to remind that this optimization is fundamentally non-convex and non-linear, so we can get stuck in local minima, which is not optimal actually. We can also have other problems like badly conditioned Hessian matrix, which you got a very flat shape at the bottom, and you can oscillate in the parameter space, so it slows down a lot the convergence. So there is a wide variety of optimizer that try to deal with this problem by using several techniques, and there is really a lot of optimizer to go through these problems. Okay, so if we apply all what we have said in the last slides to a trivial example, which is the Poiseuille Flow. The Poiseuille Flow is a 2D flow in a cylinder where you impose an inlet pressure, you got an outlet pressure. On the top and on the bottom, you got a wall condition, which means that the velocity is equal to 0. Then you can create a physics-informed neural networks with the input, which are X and Y coordinates, so the two coordinates in space. It's a steady problem, so no time coordinates. And the output are the two dimensions of velocity, U and V, and the pressure. For that, you train the neural networks with the residuals of the equations, with the boundary condition, and that's all. And so, okay, so it's okay. So in white, you can see here the training loss, which is the residual of the equation and boundary condition. And in orange, you can see the validation loss, which is basically the comparison between the prediction, and you can see that actually it converges quite quickly. But the fact is that the flow in which we are interested are fundamentally three-dimensional, unsteady, with complex patterns, and then also they can deal with vibrations of the blades in hydraulic turbines. So we have to see if pins are able to tackle these kinds of problems. Another thing that we can have in mind in the literature is that there are several possibilities of performing modal decomposition to reduce the complexity of approximation. And there are reviews, for instance, the one from Terra and others, to describe all this variety of modal decomposition. So in this master, we try to first handle the pins and to see how they work for incompressible flows. At that time, there was very few papers in the literature, so that was one of the main ideas to see in the context of incompressible flows how it performed, and also to study the parameters which affect the convergence of the pin. Then we wanted to test the ability of pins to deal with data that is not perfect, because we have the idea in mind to work with experimental information, which will be fundamentally imperfect. And finally, we wanted also to see how pins could be adapted in the architecture to source vibration caused by fluid structure interactions and also modal decomposition. So in that presentation, I presented a bit of methodology. Then we're going to see how pins can be used in the modal space, and then how the quantity and the quality of data can affect the training. And I'll end this presentation by presenting some future paths and by concluding. So to look at unsteady flows that are more complex than the trivial cases presented before with the Poiseuille flow, we choose a famous test case, which is the vortex shading around the cylinder. It's presented by this animation. You can see the horizontal component of the velocity and the wave that is oscillating just after the cylinder. Actually, this phenomena is quite typical in nature. You can see it, for instance, around islands, where you can see the shading of the vortices with the clouds, the pattern in the clouds. But it's also the case, and it's encountered around trees, around risers in the sea, around also tubes in nuclear engineering. So that's something that is quite studied a lot, and that's practical to have a test case. And to solve that, we use the pins with inputs which are space, x, y, and the t coordinates. These neural networks approximate either u, v, and p, the three components that are an unknown, and we train that using the residuals of Navier-Stokes equations, and also an error based on data. And that time we don't have exact data, and we don't have boundary condition. So we sampled data from our simulations provided by Moed Boudina in the CADIF code. Okay, so actually this is able to perform this reconstruction, but at the cost of larger neural networks and bigger training time, which is not optimal if we then want to go to three-dimensional cases, to turbulent cases, etc. So before going to more complicated test cases, we wanted to simplify a bit the approximation. And in that case, the flow is periodic, which is quite practical because we can decompose this information that is fundamentally three-dimensional into a set of two-dimensional information. So this one is the average in time. This one is the field at the first frequency. This one at the second harmonic, etc. And actually, this decomposition is mathematically this thing. So I decompose my function of space and time into a sum of function of space and function of time. And in our case, because it is periodic, we choose only sine and cosine are the function of time. And to perform this, we use the neural networks that has as input only the space coordinates, not the time coordinate that is apart. These neural networks approximate complex mode shapes, which are of a chosen number. So we choose, for instance, 3 modes in addition to the average field. And then the output is obtained by using this operation. So we sum these modes weighted by the sine and cosine function with the time arguments. And in the end, we got an approximation of the output u of x and t, which is still performed into a symbolic graph of operations, so that all our training that we presented before can be still performed in the exact same way without having to change anything. And an example of that is in that animation. So here you can see in blue the training loss, in yellow the validation loss. You can see the modes, the average modes, the first frequency, the second that perform the one that converged, the one after the other. And here you can see the exact data from numerical simulation and the pins approximation that's across the iterations of the trainings starts to look more and more like the exact data. Okay. If you look at more quantitative comparison between the classical approach and the modal one, we did several trainings where we compared the validation loss of the classical approach with the modal one. So the validation loss is basically a measure of the accuracy of the reconstruction. Here we compute the difference with the square difference with the data from simulations that we are not used in the training. And we did that for several neural networks that have different numbers of degrees of freedom. So this axis, it represents the number of parameters that you can tune in your model. So the more numbers you got, the more capable is your neural networks to approximate tiny structures, especially tiny vortices, etc. And you can think a bit like an analogy with the size of a mesh in a finite element simulation, for instance. And you can see that the classical pin, its precision increases with the numbers of degrees of freedom. And all these, just a few details also, all these computations are performed with the same the same duration of training. It's a 2-hour training in the same computational resources. And in the contrary, the modal pin approximation with only 1 frequency, 2 frequency, and 3 frequency, as soon as they are able to approximate the mode shape correctly, the precision is quite stable with the numbers of degrees of freedom, which is also interesting for robustness targets. And also, with a similar size of neural networks, you can see that with 1, 2, or 3 frequency, we can perform better than the classical pin, especially if you look at this point compared to this one, which is also quite interesting because less degrees of freedom means quicker optimization and also optimization that can be more robust. And another thing that is interesting, if we look at more details to 2 points, 2 results in this data, so one from the classical pin, one from a modal pin with 2 frequencies, and these 2 results have a similar validation loss, so a similar accuracy in the reconstruction of the flow. If you look at the forces that these results are able to predict on the cylinder, here it's the modal pin, here it's the classical pin, here it's the horizontal force, here it's the vertical force, as you can see there. The dashed line are the forces predicted by the physics-informed neural networks, and the solid lines are the exact value that we get from the simulation. We can see that the modal pin, with a similar validation loss, is able to approximate the forces, to predict the forces, so with a better accuracy, especially with the horizontal component of that, but the same conclusion draws also for the vertical component. Okay. So we talked about the architecture, but that's not only the only aspect of our work. Especially, we thought about how the quantity of data affect the training, and also there is another interest in that question is what is the interest of pins? If we provide a lot of information like this quantity of data into the training, here it's the representation in space, space, 2-dimensional space, and 1 in time. So here there is a lot of information, and actually you can reconstruct the flow field using only this, using a linear interpolation between points, and you won't get a big error by doing this. On the contrary, when you provide far less points, like here there is 10 times less point than in that case. If I provide this amount of points, it's far more complicated to reconstruct the flow field without the knowledge of physics of the partial differential equations, and that's where physics-informed neural networks are interesting and can be applied to interesting test cases. It's even more talkative when we look at data that are sparsely distributed, like in this case. So in that case, you can see that there are straight lines of data in the time dimension. So that means that we took time signals at several locations in the flow, which are depicted by the black points here. It's measurements of velocity. And around the cylinders, you got measurements of pressure. And between these points, you don't have any information, you don't have boundary condition, you only have the knowledge of the residuals of PDE. And we wanted to test this thing because this could be really the application of an experimental setup where you would measure with the hot wire pressure, with the hot wire probe, the velocity at some locations. And actually, we are also able, with this quantity of data, to reconstruct very accurately the forces on the cylinder, and it is presented in the test. And actually, this last case of sparse data is also inspired by a colleague, Thomas Charpentier, who finished his master's studies and presented today, actually. He performed experimental measurements of a flow, of a jet flow. Here you can see the jet on an array of cylinder. And he performed particle image velocimetry on that array of cylinder to characterize the flow patterns in this thing, which is of interest for nuclear applications. And the problem is that in that application, you want to make the refractive index of the water and of the cylinder match together so that you minimize the reflections of the laser in the cylinders and etc. But even by adjusting at the best that you can still have some reflection like this, which causes incertitudes, imperfections, and also which requires post-processing. So we wanted to know if it's possible to do that reconstruction using only information before and after the array of cylinders. And to do that, we performed a reconstruction using that pattern, which is a bit simplified with only 3 cylinders. We provided to the training measurement of velocity before and after, and also measurement of pressure around the cylinder that could be obtained with pressure taps, for instance. And in some cases, we are able to reconstruct the flow in between the cylinders with a good accuracy and also predict the force as well, which is quite promising for such applications. Finally, also the quality of the data is a matter of interest because with experimental application in mind, we cannot expect data as perfect as those obtained from numerical simulation. So we tested in several test cases the adding of noise, especially Gaussian noise, on which we play on the level of the noise, which is the standard deviation in our cases. And in that case, you can't match exactly the loss fitting, the parts of the loss that perform the fitting to the data and the one that perform the residual of the equation. And from the test case that we looked at, it seems that the learning is more driven by the residuals of the equation than by the noise in the data, which is also promising and can be a sign of robustness for the pins. And finally, you can also use very different types of unknown into your data. So we tested one which is an uncertainty regarding the delay of every time signals in the sparse data case. And also the pin is able to find these delays as well as reconstructing the flow in the meantime. Finally, we wanted to look at the effect of fluid structure interactions. We look at the test case of the cylinders on springs, which is excited by the shedding of the vortices, as you can see in that animation. It's a test case that is well known in classical numerical simulation methods because the fluid domain moves. And when the fluid domain moves, you have to adapt your mesh or perform immerse boundary methods. In PIN, we don't have meshes, but actually we have a set of penalization points to verify the equations. If you don't move these points, actually you will have in red the penalization points that will be inside the solid domain, which lacks of physical meaning, and also holes into your fluid domain where you don't have any penalization of the points. To address this problem, we propose several paths. One of these is to use a sampling of points that is adapted with the optimization step and with the time, but we still add some problems of convergence that would be interesting to tackle. And that's one of the future paths that we propose in future works. Another approaches would be to look at more general types of modal decomposition, like POD, PGD, and others, so that we would be able to address flows that are not only periodic, but also generally unsteady without that periodicity aspect. And finally, this could be also a way to help making the pins parametric so that it is less dependent to the configuration. It could be one pin for several boundary conditions, several operating modes, and that would be of interest for digital twins. I'd like to thank you, and I would be pleased to answer any question, either in French or English. Thank you.